Sample problem S09-05. Two skaters, a large girl and a small boy, are initially standing face to face but then push off each other. The boy ends up with more kinetic energy than the girl. A physics student who is watching makes the following contention about the forces that the boy and girl exerted on each other. Quote, since the boy has more kinetic energy, he also has more momentum, so the girl had to have pushed harder on him than he pushed on her. End quote. What, if anything, is wrong with this contention? If something is wrong, identify all problems and explain how to correct them. If this contention is correct, explain why. So we're going to jump to two things. Before doing anything, his conclusion has to be wrong. So we'll go back and see what went wrong with his premises, but the conclusion has to be wrong because we know from Newton's third law, right, every action has an equal and opposite reaction. So they have to push off each other with exactly the same force. Since he's lighter, he'll move faster, he'll have a higher acceleration, so he'll end up with a higher velocity, which is why he has more kinetic energy. But they have to push with the same force. It's physically impossible to do otherwise. A different way of justifying that, which we'll loop back here, is that since the forces they exert on each other are internal, we also know that the momentum is conserved. And the momentum at the start was 0, so momentum at the end must also be 0. So if we sort of draw these two people pushing off on each other, having pushed off on each other, and they start skittering away, where the boy goes with that velocity and the girl goes with that velocity, then we know that the mass of the girl times her velocity with a minus sign to indicate its direction, plus the mass of the boy times his velocity, in this case positive because of its direction, has to equal the initial momentum, which was 0. So we see right away that the boy does not have more momentum, he has exactly the same momentum. So where's that coming from? It comes down sort of from the following thing. The momentum is mv, but the kinetic energy is a half mv squared. So even if the momentum is the same, right, then if we reduce the mass, we must increase the velocity. But over here, the velocity goes up by twice the factor. So we can get more kinetic energy from the same momentum. A very algebraic way of looking at that, which is fine, but is entirely optional, so you can stop here and you're fine. But if we look at it this way, we can say a half mv squared, and we can always multiply anything by 1, so we multiply by m over m, which is 1, and that gives me 1/2 m squared v squared over m. And you might wonder why you would do that. It's kind of not what your freshman algebra teacher would tell you to do, but I'm making things more complicated for a reason, because now we know that m squared v squared is the same as mv quantity squared, and that's of course just p. So we end up with p squared over 2m. And so we can see that as long as the mass is changing, as long as the mass is different, then we can have the same momentum and get a very different kinetic energy. So that's an algebraic way of looking at it.